So good morning my dear students. Welcome back to my class. Today I am going to discuss about the other application of EMF measurement, that is a potentiometric titration. That is, potentiometric titration is defined as the titration between two solutions in order to find out the endpoint of the titration by monitoring the change in the potential around an indicator electrode. Okay, or simply the titration that involves the measurement of the change in potential so as to find out the endpoint of a reaction is called potentiometric titration. Here, two solutions are allowed to react in a quantitative manner. One solution, that is the solution to be titrated, is taken in a cell in which an electrode called indicator electrode is introduced, which can respond. The indicator electrode can change its potential with respect to the concentration of the ion present in the solution. Okay, and another solution is allowed to add from a burette, that is a titrant. The titrant is allowed to add from a burette. As the titrant in small portion is adding or introduced into the solution in the cell or beaker containing the indicator electrode, there occurs a change in the potential as shown by the indicator electrode due to the change in the concentration of the ion. And this potential is monitored. Okay, the change in potential is noted with respect to the addition or volume of the titrant to be added. Then the graph is plotted between the change in potential versus the volume of the titrant added. At the end point, there is a sudden change. Okay, that is the breaking point. At the end point, there is a sudden change in the potential occasioned by the addition of a very small volume of the titrant into the solution. That can be easily determined as the point of inflection from the curve, from the graph. That is the principle. Actually, the indicator electrode is connected to, joined to a standard calomel electrode, saturated calomel electrode, so as to form a complete cell, and the EMF of the cell is measured. Okay. Actually, the change in potential around the indicator electrode is measured in the form of EMF of a cell connecting the indicator electrode to a saturated calomel electrode, and it is measured potentiometrically. And the EMF is then plotted against the volume of the titrant. There is a gradual change in the EMF when the endpoint is attained, responding to a small volume addition of the titrant. There occurs a sudden change in the potential. That is the endpoint in the case of potentiometric titration. The point at which there is a sudden change in the potential by the addition of a very small volume of the titrant is called usually called the endpoint or breaking point of the potentiometric titration. So usually the solution to be titrated. So depending on, we can classify there is a various type of potentiometric titration, or we can find out the endpoint of various reaction potentiometrically. One is acid-base titration, usually acid-base titration. Okay. Then second, redox titration. And three, precipitation titration. These are the three major titration that are followed by measuring the potential or EMF, change in potential or EMF of the solution. The acid-base titration, in the case of acid-base titration, for example, HCl against NaOH. The acid, the solution will be titrated, acid is taken in a cell. It is taken in a beaker or a cell, a definite volume okay, definite volume V1 of the acid of HCl. Acid is taken having particular concentration, having concentration N1, is taken in the cell or a beaker. Okay. And a glass electrode, usually you know that here the indicator electrode that respond to the change in H plus ion concentration, change in potential with respect to H plus ion concentration is usually hydrogen gas electrode or a glass electrode. Usually we can generally say a hydrogen gas electrode. An hydrogen gas electrode or a glass electrode which is used as an indicator electrode whose potential changes with the change in the hydrogen ion concentration. So usually the acid-base titration, the indicator electrode employed is an hydrogen gas electrode or a glass electrode whose potential changes with respect to the concentration of H plus ion or change in the concentration of H plus ion. And this indicator electrode is then connected to a standard saturated calomel electrode so as to form a cell assembly, and the EM of the cell is changing. EM of the cell is monitored potentiometrically by the addition of the alkali or NH from the microburette or burette. Okay, in which that is second is indicator electrode. This is the indicator electrode. This is hydrogen electrode, glass electrode. Okay, this is assembly platinum. This is a hydrogen gas electrode. Okay, this is an hydrogen gas electrode which is dipped or glass electrode, and in which NaOH is added from the burette. NaOH is added from the burette. This is alkali. And alkali in most cases is a standard, okay, of no volume, okay, normality N2, that is standard. Then on adding, you have to remember the reaction, you have to note the important point is that in the acid-base titration we are employing the indicator electrode. Is one that respond with respect to the change whose potential changes with respect to the concentration of H plus ion. Usually the hydrogen gas electrode is employed or a glass electrode is employed, and the reaction is reversible, is an electrode that is reversible with respect to the hydrogen ion. The reaction employed in this case is acid-base titration. In the case of acid-base titration, the reaction employed is H plus aqua plus, okay, of concentration C plus electron reversibly gives half H2 gas. Half H2 gas, and you have the E H plus bar H2 is equal to E0 H plus bar H2 minus 0.0591 by N1 by 1 log half H2 is 1 divided by H plus, and that is equal to, this is 0 standard, okay, the standard potential of hydrogen gas electrode is 0 plus 0.0591 log H plus, and that is equal to, that all of you know that pH is minus log H plus. So we can write this is us minus 0.0591 pH. Okay, this is thus the hydrogen gas electrode, there is a potential that is proportional to the pH of the solution, and this hydrogen gas electrode assembly is then connected to, coupled with an SHG like this: platinum, hydrogen 1 bar, hydrogen gas 1 bar or 1 barometric pressure, H plus aqua, okay, it's here, or H plus aqua, double vertical line, that is you took the containing, that is salt which, okay, is connected to KCl saturated solution, KCl aqua saturated. Then Hg2Cl2. Hg. This is the cell assembly. So this is the indicator electrode, hydrogen gas electrode, glass electrode, which is acting as the anode, by this acting as the cathode. Acting as the cathode. Then the HCl is taken in the cell or burette, and into which the electrode is immersed, and NaOH is added from the burette in small volume, so that it develops a potential. The hydrogen gas electrode develops a potential depending on the H plus ion, which is measured as the EMF of the cell assembly. The EMF of the cell, E cell. The EMF of the cell assembly, E cell, measured potentiometrically, is equal to E right minus E left, or E cathode minus E anode. That's equal to 0.2415. Okay, that is the cell assembly. That is E saturated calomel electrode minus E hydrogen gas electrode. That is equal to 0.2415. 2415 minus 0.0591 pH. That is equal to 0.2415 minus plus 0.0591 pH. So this is the equation. That is, on adding NaOH into the HCl solution, that is during the titration, the EMF of the cell going on increases. The EMF of the resulting cell going on increases with the addition of NaOH into the solution, so that the plot of around plotting, that is plot of E cell versus volume of NaOH, volume of alkali added. It is going on increases. You know that? Initially, it is going on increase like this. This is as this is the low potential. Okay, as a low value of the EMF, as we are adding, this goes slowly increases, and corresponding to a particular point, that is the corresponding end point, there is a sudden change in the potential like this. There is a sudden change in the potential, and that is also gradually going on. It's like this is the variation of the potential, and this point of inflection, the volume corresponding to the point of inflection, the volume of NaOH corresponding the point of inflection gives the sudden change in the potential, that is end point. Okay, that's it. The volume corresponds to the point of inflection. Volume, okay, have it right. The volume, the V, volume of NaOH. NaOH correspond to the point of inflection. Point of inflection. Okay, that actually gives the breaking point of sudden change. Give the end point. That gives the end point. So the end point, we have the equation V1 N1 is equal to V2 N2. Thus, by knowing V1 N1 of the acid, and by measuring the volume V2 of the alkali at end point, we can calculate N2, the NaOH, the concentration of normality of NaOH like this. Or by knowing the volume of, measure the volume of standard alkali and this normality, and by knowing the volume of the acid, we can measure the normality or strength of the acid. Okay, that is the acid-base titration. So this is the equation here. I hope that you have followed. That is, when the addition of NaOH in the solution results in the gradual increase in the E cell, the resultant E cell of the that is potential EM of the resultant cell constituted, and at the end point there is a sudden change in the EM of the solution, EMF, by the addition of very small volume of energy. Okay, that is the situation. That is with very small change in the, by a small addition of energy, correspond to a very small addition of energy, there is a sudden change in the potential or EM of the solution, and so that the point of inflection correspond to that, give the volume of the energy correspond to that point of inflection, give the end point. Then we can find out this equation, we can find out the strength of the one of the solution by knowing the other three factors. So the acid base. So usually this is employed for the acid base titration. And second is redox titration. Redox titration. A redox titration, this is usually called oxidation reduction titration. Example is when ferrous sulfate or ferrous ammonium sulfate is titrated against ceric sulfate. It is converted to ceric sulfate. Reduce oxidizes ferrous to ferric. Fe is 2 plus A, converted to ferric, while ceric is reduced to Ce2 plus. Okay, Ce3 plus. Okay, like this. See, that's the situation. Here, the reaction is the titration of Fe2 plus Ce4 plus react to gives Fe3 plus and Ce3 plus. It's an example of a typical redox titration. We can follow this redox titration by employing an indicator electrode like a platinum electrode that will respond the ferrous ferric redox titration change in potential. So here we have used the redox indicator. Redox electrode, redox single electrode. Redox single electrode is employed as the indicator electrode, that is a platinum electrode, a platinum wire is dipped into a solution of Fe2 plus ferrous ammonium sulfate containing little ferric. Automatically this is implied as. So this is the situation: platinum, Fe2 plus, Fe3 plus. Okay, this is the situation. And this is then coupled with a saturated calomel electrode. This system is then connected to a saturated calomel electrode. So as to form a cell. And the EMF of the cell changes on the addition of ceric sulfate or ceric ammonium sulfate from the burette, which is a titrate. Okay, here the volume to the solution to be titrated, that is ferrous ammonium sulfate. For volume V1 is taken in the cell or the beaker. Okay, to which a platinum wire is dipped or immersed. Then ceric ammonium sulfate Sce4 plus, the titrate, is added into it from the burette in small volume. Its small volume usually 0.2, 0.3 or 0.1, 0.2, 0.3 etc. volume. And the change in the EMF is noted. Here, when we are making such an assembly, here the platinum ferrous electrode acting as a anode, while while the calomel electrode acting as the anode. The potential is such that when we design such an electrode, the assembly is like that. That is, we have the Hg, Hg2, Cl2 solid, then hyphen KCl aqua saturated. This is the saturated calomel electrode. There is a double line indicate the salt bits. Then is connected to platinum. Okay, this is the redox solution, that is ferrous or ferric, Fe3 plus bar Fe2 plus, then platinum. This is the situation. Okay, Fe plus aqua, Fe3 plus aqua, Fe3 plus aqua, connected to Fe2 plus aqua. This is the, actually we have a solution of ferrous iron, ferrous ammonium sulfate in contact with the platinum, to which we are adding ferric sulfate from the burette. Ferric sulfate from the burette, so that ferrous is converted to ferric, and thus we have a redox electrode here form, constant redox platinum redox electrode containing ferrous and ferric. On the addition of ferric sulfate from the burette, more and more ferrous and is converted to ferric, so that the potential going on increases. And as a result, we can monitor the change. That is the volume. Okay, this is the EMF, ESL. And this is the volume of ferric sulfate, C4 plus. And the reaction employed is, you know that is E cell is equal to E cathode minus E anode. That is equal to Fe 3 plus bar Fe 2 plus minus 0.2415. This is the equation. As the titration proceeds, progressing, on the addition of ferric sulfate into it, this potential going on increases. This remain constant, so that the EM of the cell increases as such. Okay, as this value increases, as the titration is progressing, because C4 plus converted more ferrous into ferric, so that this potential going on increases. So we have the E cell increases. So that is the situation. So on adding ferric sulfate into ferrous ammonium sulfate, the EM of the cell going on increases on the addition of the ferric sulfate, and at the end point, by the small addition of ferric sulfate, there is a sudden change in the potential, and this can be monitored. The point of inflection corresponding to the volume of the C4 plus corresponds to the volume of point of inflection, the volume of ferric sulfate, C4 plus corresponds to the point of inflection, give the end point, from which using this equation we can find out the strength of either ferrous sulfate by knowing V2, N2 and V1. So that is the direction. So this is the situation. Okay. So any redox titration can be employed here. The indicator electrode is a platinum wire dipped into the redox system. It's acting as the indicator electrode or solution to be titrated, to which a platinum electrode is introduced, which is dipped in the solution. Okay, and the titrate is added from the burette, so that and the whole assembly is connected to a calomel electrode, so that calomel electrode acting as the anode, while redox system acting as a cathode. So on adding the titrate into it, that means the progressing the titration, the potential of the cell or the EM of the cell going on increases, and the end point there is a sudden change in the potential by a small addition of ferric sulfate or titrate. That the volume corresponds to the point of inflection is the end point from which we can calculate the strength of the one solution by knowing the strength of the other solution, the volume mass. V1 N1 is equal to V2 N2. Therefore, N1 is equal to V2 N2 by V1. Okay. Then this is redox titration. Redox titration is precipitation. precipitation titration. Okay. That is here, when one reactant is added into the another reactant into which an indicator electrode is introduced, the precipitation takes place so that the concentration of the ion decreases as the precipitation is progressing, so that the EMF around the indicator electrode or the potential around the indicator electrode gradually diminishes with the addition of the titrant into it. So by monitoring the change in the potential, the decrease in the potential as the precipitation is going on, we can find out the endpoint of the titration. Example is the reaction between AgNO3 and NaCl. The reaction between Ag silver nitrate and NaCl giving AgCl precipitate plus, okay, this is a precipitate, plus NaNO3. This precipitation titration can be monitored very well potentiometrically. Here, the AgNO3 is taken in the burette. AgNO3 is taken in the cell or the beaker. A definite volume of particular concentration of AgNO3 is taken in the cell or burette or cell or beaker, to which a silver chloride electrode is dipped, into which a silver chloride electrode. The cell assembly is such that there is AgCl solids, then there is KCl. So this is actually the electrode assembly that is we are using, KCl or NaCl. Okay. AgNO3, or we have to, okay, AgNO3 aqueous electrode. Constitute. Okay, silver nitrate electrode. Okay, we have to a silver nitrate. Okay. We are actually making assembly AgNO3 assembly here. A silver electrode acting as indicator. Electrode is dipped into the silver nitrate solution. Then, which is then connected to the saturated calomel electrode. So our indicator electrode in this titration employed is silver nitrate electrode, or silver electrode dipped in the silver nitrate solution. Okay, a silver electrode, Ag electrode dipped into it, and NaCl, the titrant is added into it, its mole volume, so that then it is connected to assembly with the saturated calomel electrode, and the cell assembly is like that. There is Hg2Cl2 solids, G2Cl2 solids, then KCl saturated aqua, saturated, that is solid which it is connected to AgNO3 aqua. This is a cell in the solution, but Ag. This is our electrode assembly. That is, NaCl is added from the burette. So that AgNO3 get precipitated. And it has a cell EMF. E cell is equal to E cathode minus E anode. That is equal to E Ag plus bar Ag minus, this is 0.2415. Actually, when we add NaCl into it, when NaCl is added into it, AgNO3 gets precipitated as AgCl solid plus NaNO3. So that as the concentration of Ag plus ion diminishes on the precipitation of Ag as AgCl. So on adding NaCl into the solution, AgNO3 is converted to AgCl precipitated. Okay. So that the concentration of Ag plus ion in the solution decreases so that the potential gradually decreases. So that E cell decreases, the situation. So as the titration proceeds, when adding more and more NaCl needs, what is the situation is that the EMF of the cell gradually diminishes because of the decrease in the concentration of Ag plus ion, because Ag plus ion gets precipitated as AgCl, so that its potential gradually decreases like this, and finally you have to remember, finally, by a small addition of this NaCl, there is a sudden decrease, and going on like this. This is the situation. And this is the situation monitoring, when we monitor like this. This is the changing potential. So the point of inflection corresponds to, you look here, the volume of NaCl, the volume of here potential E cell is plotted against the volume of NaCl. The volume of NaCl corresponds to the point of inflection gives the end point, from which we can write this equation V1 NaCl V2 N2, so we can find out the strength of silver nitrate N1, knowing the volume of NaCl, normality strength of NaCl and volume of AgNO3. So that's the situation. This is the precipitation idea. Here the principle is that as the precipitation is going on, the potential gradually decreases so that the EMF of the cell constituted by the indicated electrode going on diminishes, and the end point there is a sudden decrease from which we can find out the end point. Example is titration of AgNO3 against NaCl so as to find out the strength of AgNO3 solution. The next we have to discuss about So next we have to discuss about the corrosion of metals. So we can discuss this aspect the next class. What is meant by corrosion of the metal, classification of corrosion, theory of corrosion with the examples with respect to the rusting of iron we have to discuss according to your syllabus, and the mechanism or the various method for the elimination of corrosion in the metal. So we will discuss this in the next class. Thank you very much for listening me.